the summation of all the oxidation numbers has to equal the charge on the compound. If it's a neutral compound, yes, it has to equal 0. But if it's a charge, like sulfate ion, SO4 2-, then it has to equal 2-.
What about KCl, doctor?
KCl,
Yes.
it has to equal 0. So KCl is -1, potassium is +1. Those are your oxidation numbers.
Oh, hold on. Was it KCl that I'm? No, I don't think it was KCl. I'm wrong then.
Was that the one?
No, I'm opening it up on my laptop.
Okay. We'll do that, then we'll start on chapter 12 as soon as you get that.
Let me see. It's so much information. You finish one chapter and then there comes another one and then there comes the final. So you really don't, me personally, I don't have time to go over.
That's the same for a lot of people.
And it makes me more and more nervous.
Yeah, summer classes are extremely hard because of that. There's a lot of information in a short period of time.
Yeah. Okay, so let me see it here.
All right.
Right here. It is KClO3. So I'm trying to make it equal 0.
Right.
And I'm putting in +1 for the K, -1 for the Cl, and for the O, it's always a -2.
No. Oxygen is -2. That's your first one.
Yeah.
Okay.
And then
chlorine is -1. Then you solve for K.
It's,
so
which is +1.
No.
No.
It's -6, -1, plus whatever K is has to equal 0. It's either K or C. Which one's first? Is it in this chapter with the rules on it? But you got to have one of these.
It's on chapter 14.
Oh, chapter 14?
Yeah, I have a +1, which is marking me right for the potassium, and a -2 for the oxygen.
No, oxygen, there's an order of assigning it. Anyway, it's either potassium or chlorine. I don't want to tell you the wrong one. Okay. Right, okay. I did it right. All right, so you know oxygen's -2.
Yes.
And chlorine is -1. Now you solve for potassium. You don't know what potassium is. So you got a -6 charge for the 3 oxygens, right? There's three -2 charges. Right?
I have a -2 for that one.
Right, but there's 3 of them.
Oh, okay. Oh, I see what you're saying.
Chlorine's -1. Then you solve for potassium, which you don't know. And you set it equal to 0 because 0 is in charge on the compound. So the charge on K is going to equal +7. So K is +7, Cl is -1, and oxygen is -2 for your oxidation numbers.
I see what you mean.
That when you add everything together, it equals 0. 7 -1 -2 3 times is equal to 0. So the oxidation number on potassium is +7. Again, oxidation numbers don't mean anything. They're just used to show transfer of electrons in oxidative states. They're not a real number to assign to something. They don't mean it's a +7 charge or anything like that. This is an oxidation number. They have no real value.
I got it.
That makes sense?
Yeah.
All right.
So the the O3 is. Okay, I see now.
Okay, perfect.
Making me nervous because I'm like, I
Oh,
don't.
no problem.
Okay,
All right, let's do chapter 12, then we'll get to some questions. All right, so we're doing acids and bases. Okay, there's different ways to define acids and bases. One way is the Arrhenius definition. There's Arrhenius and then the Browstead-Lonery definition. The Arrhenius acid is acids give off or produce H+. Bases give off or produce OH-. So according to the Arrhenius definition, if it's an acid, it's going to donate H+ into solution. If it's a base, it's going to donate OH- into solution. That's this definition. So whenever we have a high concentration of H+, we're going to be very acidic. We have a high concentration of OH-, we're going to be very basic. Some common acids and bases, if they're names, like with that, I'm going to get my right here. So like you have hydrofluoric acid, hydroiodic acid, hydrobromic acid, and hydrochloric acid. Those are the halogens. Okay? The other ones are using the polyatomic ions in combination with hydrogen. Okay? Whenever you do with acid, you write the H first. So carbonic acid would be H2CO3. Carbonate ion is CO3 2-. Okay? Nitric acid, HNO3. Nitrate ion. Okay? Phosphoric acid, H3PO4, phosphate ion. Remember, phosphate has a -3 charge. Okay. Acetic acid has a hydrogen and then C2H5. C. Where are they calling it? They're written down the wrong. H5O2. C5H3. Right, acetic acid is CH3. All right. C2H3O2, acetic acid. The acetate ion. And it's a -1 charge, so there's only 100. Common bases like sodium hydroxide, magnesium hydroxide, calcium hydroxide, anything with OH is usually a base. Okay, so those are the Arrhenius definitions of acids and bases. What else do you want to cover? Dissolves in solution. You'll see it written different ways. Still means the same thing. You'll see it written with water. Let's say hydrochloric acid goes to H+ plus CO-. You'll also see it written dissolving in water, which is that's just a shortcut word. HCl plus water, because it dissolves in water, goes to H3O plus CO-. Those are the exact same things. Okay? The water is absorbing the H+ ion. Remember, water is H2O. Okay? And another hydrogen is bonding here, giving it a positive charge. Okay? So H+ is the same thing as writing H3O+. It's the same thing because the H bonds to the water, making it acidic. All right. So let's take some example from the book and write some equations here. Let's take hydrobromic acid plus water. HBr plus water. Okay, it's acidic. Okay, so you're going to get the hydronium ion, H3O plus Br minus. Okay. So we got magnesium hydroxide dissolved in water. Magnesium hydroxide is a base. Goes to Mg2 plus 2 OH minuses. So you're producing OH, it's a base, you're producing H plus, That is an acid. And it can be written as H plus or H3O plus. Now, when you look at hydrobromic acid, there's only one hydrogen. You can have multiple hydrogens. Okay. You can give off different products. Battery acid is H2SO4, sulfuric acid. So H2SO4, let's do plus water, can go to HSO4 minus, that's given off plus H3O plus. Okay, it gave off one of its hydrogens. Okay, the HSO4 minus can react with water again to give off a second proton to give you SO4 2 minus plus H3O plus. Okay. So both hydrogens can be delivered into solution. That's called a diproduct acid. Monoproduct is one hydrogen, diproduct is two hydrogen. Polyproduct means multiple. Like phosphoric acid. Phosphoric acid is H3O plus. It can give off one hydrogen, then another, then another. It has three hydrogens to give off. So H3PO4. Each step can give off one hydrogen. Those are called polyprotic acids. So there's a first ionization, a second ionization, and a third ionization for phosphoric acid. Okay. Where are we at? All right, so far so good. Another definition of an acid is what's called the Bronsted-Lowry definition. An acid, okay, donates H plus ions, which is what the other one did. On a base, accepts H plus ions. Slightly different destination, but they can do the same thing. So if you had water plus HCl, H2O plus HCl, again, goes to H3O plus Cl minus. Okay, this right here, hydrogen, was donated from HCl to the water. So it donated an H plus. So it's an acid. Let's take ammonia for another example. NH3 plus H2O goes to NH4 plus OH minus. So water donated hydrogen to NH3. So the base is NH3 because it's producing OH minus. So this is a base, ammonia is a base. It produced your OH minus. And the water donated a proton, the NH3 accepted a proton. It accepted the H plus. Okay? So it's a proton acceptor, makes it a base. Okay, it accepted that H plus. So the similar definition is just slightly different how you look at them. Okay. So if you look at, let's look at a reaction here. Let's say, let's clear these and let's do H2S plus water goes to HS minus plus H3O plus. Okay. Now one is an acid, one is a base, because one is donating a proton, one's accepting a proton. So is H2S, this is our first one, this is our second one. Is number one or number two donating a proton, giving one off? Proton is an H. So which one's losing an H?
Number one.
Right, perfect. So this is your acid. Okay. Number two is accepting a proton. So this is your base. It's an acid-base reaction. Okay. Water can act as an acid or base depending on what it's being reacted with. So in this case, reacting with H2S, the water is acting as a base. It's accepting a proton. Remember, acids donate a proton. Let's take one a little not so clear here. Let's take HCl plus C2 H6O goes to C2 H6OH plus CO minus. Again, 1 and 2. Which one's the acid, 1 or 2? Which one's giving up an H?
Number 1.
Number 1, perfect. HCl is your acid. Okay. What's your base?
Number 2.
Number 2. This is accepting a proton, so that's your base. Acid-base reaction. Okay. So you just gotta remember, water can be an acid or a base depending upon the reaction. We did NH3, remember? Let's do NH3 plus water goes to NH4 plus OH minus. Okay. We'll do number 1, we'll do number 2. Okay. Number 1 is what? Acid or base? What's it doing?
Is it accepting a proton?
Yeah, it's going from NH3 to NH4. It's gained an H. It's accepting a proton. So this is your base. And water's doing what? Water's giving up a proton. This is your acid. So like I said, water can serve as an acid or a base, depending on what you're reacting it with. Okay, perfect. All right, we're going to talk about equilibrium. Equilibrium is when something comes to rest. You know, with all these reactions we're looking at, go in both directions. They go forwards and they go backwards. And when equilibrium, the forward reaction is equal to the reverse reaction. Everything is stable. So when you miss an acid and base, they're going to give you a salt and water. As that reaction goes across, it's going to go one way, then the other way. And when it gets to equilibrium, that's when both reactions are exactly the same. Strong acid, equilibrium favors going almost all the way. A very weak acid, equilibrium favors the reactants. It doesn't go as far because it's a very weak acid. Okay. So if we put in, let's get rid of some of these. If I put in HCl, which is a very strong acid, you get H plus Cl minus. It goes both ways. 99%, close to 100%, is H plus and Cl minus. If I put in a weak acid, hydrofluoric acid, okay, goes to H plus F minus, about 98% is going to be H plus, 2% is going to be your dissociated ions. It's a very weak, it doesn't break apart as much. It's a very weak acid. So at equilibrium, 98% is about is HF, the compound. At equilibrium HCl, 99% is H plus and Cl minus because it breaks apart almost 100%. So that's a weak acid and a strong acid. So that's what equilibrium is. Equilibrium is reaction goes both directions. And in equilibrium, it's where everything is stable. It's when you reverse the forward reaction rate is equal to the reverse reaction rate. Okay? We'll talk about different reaction rates as we go down through the chapter. Okay. Let's take a couple examples of things. So now we know what acids and bases are. We have things that are called conjugate acids and bases. And that's just, conjugate just means reverse. That's all it means. It's a reverse reaction, talking about equilibrium. So let's take an acid. Let's take a weaker acid, H, C2, Cl3, O2. Let's take that as an acid. Plus water goes to, we can go both directions, H3O plus and C2, Cl3, O2 minus. Okay. So look at this side here, number 1, number 2, number 3, number 4. Okay. Look at our reaction going from left to right. What is number one, acid or a base? Does it give up a proton or accept the proton? Proton just is hydrogen.
It gives up a proton.
Gives up. It's an acid, right? And this accepts a proton. This is your base. The word conjugate just means going the other direction. So this is our conjugate. And what does it do? Look at the reverse reaction going from right to left now. Does H3O plus going backwards give up a proton or accept the proton?
It gives up a proton.
So it's a conjugate acid because it's giving a proton. And this is a conjugate base because it accepts a proton going right to left. So just look at your reaction. All the word conjugate means is backwards. It means reverse reaction. And the acid and base are still the same definitions. Acids give up proton, bases accept the proton. It means it's going the opposite direction for equilibrium. That's what conjugate means. So you can be any reaction, acid base, you can determine what's a conjugate acid, what's a conjugate base. Okay, let's do one that's not as easy to identify. Identify the acid base pairs. Okay, what do I want to get this done here? All right, let's take HBr. This is from your book here. Plus equilibrium reaction goes both directions to okay. I'm going to label one. Maybe I'm going to label one. 1, 2, 3, and 4. Okay, so number one, acid or base?
It gives up a proton.
So
Right.
it's a what?
Would it be acid?
Perfect. Perfect. Acids give up proton. So this is your acid. So number two is what?
Base.
Base. It accepted the proton. Now going the opposite direction. So we put conjugate because that means we're going backwards now. We're going from right to left. Okay. So number three is what? A conjugate. What does it do?
It's a base.
Does it accept a proton or give off a proton?
It gives up a proton.
It goes from CH5O to CH4O. It gives off a proton. So giving off a proton makes it a what?
Oh, an acid.
Perfect. Conjugate acid. And this accepts a proton. This is your conjugate base. So conjugate means just going in the opposite direction for equilibrium. So you got acid, basis, conjugate basis. And all it has to do with is giving up or accepting a proton. Okay. We got that. We got that. Okay. We use these a lot of times as buffer situations, like with buffered aspirin, things like that in medicine. Like we'll take carbonic acid. Let's take carbonic acid. And one of your equations says carbonic acid is a weak acid, which means most of it's going to be reaction. It says write equilibrium equations showing the acid reaction to H2CO3. Goes to what? What's our acidic reaction? This gives off a proton to go to HCO3 minus, okay, plus H3O plus. Okay, so you have an acid and the water is your base. And this is your conjugate base, right? Now the conjugate base can accept a proton like it does an inverse reaction. So if you want to write another reaction to it, you could say HCO3 minus, okay, which is your conjugate base, plus H2O goes back to H2CO3 plus H2O. And you just wrote the reaction backwards, which is the same thing. So now this is your base because it's accepting a proton. This is your acid because it's donating a proton, H3O plus. Let me write that there. This is, takes in H2O plus, H2O3, OH minus. Sorry about that. Okay. So this shows it's your conjugate base, just like it was, and it's accepting a proton if you water your acid. So you can write the reactions in reverse direction, showing your base or conjugate base. And those are reactions that occur in the body to buffer the solution, which we'll talk about in a little bit. Okay. Everybody understand the difference between conjugate acid and conjugate bases, and acids and bases?
Yeah.
Okay, perfect. Okay. All right, we talked about neutralization reactions before. Okay, we have an acid and a base, gives you a salt and water. So let's put an acid, hydrofluoric acid, okay, plus a base, say sodium hydroxide, goes to your salt, NaF, plus H2O. So it always produces, neutralization reaction always produces salt and water. And we'll do it with any of them, okay? And your net ionic equation is always going to be H plus OH minus goes to H2O, because the salts are soluble in water, so your spectator ions cancel out. So this is always going to be your net ionic equation for a neutralization reaction. That's what we call neutralization reaction. Okay, because the H plus and the OH minus go to water. Okay. And like I said, we've done those before. That's our net reaction. And let's do one. Let's do example 12.3 in your book. It says write a balanced equation for the reaction of nitric acid and calcium hydroxide. Okay. So let's write that out. We'll show you the 3 different reactions. So nitric acid is HNO3. And I said calcium hydroxide, right? Calcium hydroxide is calcium hydroxide. Okay, and this can produce your salt, which in this case is calcium nitrate plus water. Is that balanced? No. We need 2 NO3 groups, so let's put a 2 here. And is that balanced? Well, how many hydrogens we have? 4. So we have to put a 2 in front of the water here, right? For 2 oxygens, 4 hydrogens, 2 nitrates, and 1 calcium. All right. That should be balanced, right? That's your balanced molecular equation. Now write your total ionic equation. Break them into ions. You break this into ions, you have 2H plus 2 NO3 minus plus Ca2 plus 2 OH minus. Right? Break it into ions. Then your salt, you break into calcium 2 plus 2 NO3 minus plus 2 H2Os. That's your total ionic equation. Then get rid of your spectator ions, which are NO3, calcium, and you get your net ionic equation. Your net ionic equation is H plus OH minus goes to H2O. And that's the net ionic equation for all neutralization reactions. We give you salt and water. Like I said, we've done those before. We can do another one if, well, let's see where we at. Okay, let's do one more, then we'll do reactions with single elements. So write a complete ionic equation and a net ionic equation for the neutralization reaction of barium hydroxide. Barium hydroxide is BaOH2. And we react that with nitric acid. And it's going to form your salt, which is barium nitrate. And HOH, which is water. You take the OH from the base and the H from the acid. Everybody sees how to do that, right? Yes, no, maybe.
Yeah.
Okay. And we got to balance it. We've got 2 nitrate groups. You got to put a 2 in front of the here. And we've got 4 hydrogen. Got to put a 2 in front of the water here. And that should balance it. Okay. They want to write the total ionic equation, which is the complete ionic equation. So Ba2 plus 2 OH minus. Okay, barium breaks apart and the nitric acid breaks apart. 2H plus 2 NO3 minus. Okay. And then the other one, salt breaks apart, Ba2 plus 2 NO3 minus 2 H2Os. And again, get rid of the spectator ions. And you're left with H plus OH minus goes to H2O. So you got your balanced molecular equation on the top. You got your total ionic equation in the middle. And you got your net ionic equation on the bottom. And I guarantee you'll see questions of that on your final exam. Just write those 3, you have to identify those 3 equations. Where'd I go? All right, perfect. Okay, so those are basically double displacement reactions. 2 things are being switched. Okay. Single displacement reactions are when a metal reacts with an acid. Okay. So you can have, say we got iron, metal, which is a solid, plus we put it in hydrobromic acid. Okay. We end with Fe Br2 plus hydrogen gas is given off. So the metal, the iron, has replaced the hydrogen to give you iron 2 bromide. Okay. That's a single displacement reaction. Okay. Your ionic equation is Fe solid plus H plus Br minus goes to Fe 2 Fe2 plus 2 Br minus plus H2 plus. Bromines cancel, and you're left with Fe solid plus H plus, which is your acid, goes to Fe2 plus hydrogen gas. Okay, so a little bit different, but still the same concept. You got your molecular equation, you got your total ionic equation, and you got your net ionic equation. Okay? The net equation is crossing out the spectator ions. Okay. Now you have to use what's called an activity series to see if that reaction will occur. Because sometimes the metal is not strong enough to replace the hydrogen on the acid. In other words, you look at it, what's called the ionization table. I'll show you that in a second. I think you have one in your book. In other words, if you took magnesium and reacted with hydrochloric acid, it should produce magnesium chloride plus H2 gas. If you took zinc, reacted with hydrochloric acid, it would produce zinc chloride plus H2 gas. If you took gold solid and placed it in hydrochloric acid, you get no reaction. The gold doesn't replace the hydrogen to produce hydrogen gas. Okay? So acid doesn't dissolve gold, which logically we know, but you're not going to dissolve gold with acid by pouring acid over it. Okay? So we look at what's called an activity series to do that. And our activity series is in the next chapter. I don't have it pulled up here. Okay. So certain ones will react, certain ones won't. It depends how active the metal is, how easily it is to oxidize it. Okay. Remember, oxidation is the oxidation is the loss of electrons. Reduction is the gaining electrons. We'll go into oxidation reduction in just a minute here too. So let's take some metals that will react and let's show you what they do. Let's say we react calcium with sulfuric acid. Okay. What's that going to form? Okay. Remember the positives replace that. So you get calcium sulfate plus hydrogen, H2 gas. Aluminum reacts with nitric acid. Okay. Aluminum replaces the hydrogen. Aluminum nitrate plus H2 gas. Okay. And you have to balance out. That one was balanced. This one you have to have 3 NO3s. So put a 3 here. And then 3 hydrogens, so I have to make that 6 actually. To make this 6 hydrogens. And a 2 here, and a 2 here. And that should balance. 2 aluminums, 6 hydrogens, 6 hydrogens, 6 NO3 groups, 6 NO3 groups. Okay, so those are single replacement reactions, metal and, okay, shows how metals react with acids. Acids can also react with water. That causes one of the big problems in our environment, acid rain. Okay. A lot of our automobiles produce SO3 gas. That's one of the byproducts of your combustion, the sulfur trioxide. Sulfur trioxide gets in the atmosphere. There's water in our atmosphere, right? SO3 reacts with water, H2O, to produce H2SO4. Okay, so sulfur trioxide is not a problem, but once it's reacted from your car engine, okay, it reacts with the water in the atmosphere, produce H2SO4. H2SO4 is battery acid, a very strong acid. That's what causes acid rain. It gets into our environment. So when it rains like that, you're actually in polluted cities, it's raining sulfuric acid. That's what your lungs are breathing. And that will destroy lung tissue, destroy statues, it destroys our buildings. Okay. These are things released from our automobiles when we drive them. Dinitrogen pentoxide is also released as one of the byproducts of combustion of fossil fuels. N2O5. Okay. Again, that reacts with water in the atmosphere. Okay. And that produces HNO3. Which is nitric acid. Again, nitric acid is a very, very strong acid. And what it's going to do is produce acid rain. It's going to get in there, destroy statues, destroy buildings, and destroy your lungs when you breathe it. So these are the two main components of acid rain, sulfuric acid and nitric acid, from byproducts of burning fossil fuels. Okay. Let's get to the next section. All right, now we're going to start with some of the pHs and some of the math, some of the problems you guys were having with the H plus concentration. So remember, as the H plus concentration increases, the strength of the acid increases. Okay. As it decreases, the strength of the acid decreases. Remember, neutralization reactions always produce an acid and a base, always produced salt and water. Thanks, Dalton. So when we produce our salt and water, we're producing a neutralization. It gets to neutral. Neutralization, okay, is at 10 to the minus 7. 1.00 times 10 to the minus 7. H plus concentration is neutral. That's when the acid and the base react to form salt and water. You got water, which is neutral. Okay, this gives you a pH equal to 7. These are our neutralization points. Okay. As the acid concentration goes up, it becomes acidic. As the acid concentration goes down, it becomes basic. Okay. So remember, neutrality, okay, is when they're both equal to 10 to the negative 7. So the concentration of H plus times the concentration of OH minus is always going to equal 1.00 times 10 to the negative 14. That's one of the equations we're going to use. Okay? The H plus times the OH concentration is always going to equal 10 to the minus 14. When it's neutral, the H plus and the OH are the same, right? You don't have an acid, you don't have a base. If they're the same, H plus is 10 to the minus 7, OH is 10 to the minus 7. That's your neutral point. You multiply them together, you get 10 to the minus 14. They're both the same. As the H plus goes up, the OH goes down. That's acidic. If the H plus goes down, OH goes up. That's basic. You can always multiply them to equal 10 to the minus 14. Remember, brackets around something mean concentration.
I'm sorry, what's basic? Is it the pH equals 7? That would be basic?
The pH equals 7 is neutral.
Okay.
Okay. When pH equals 7, we haven't quite done the pH yet, but we're getting to pH equals 7. The H plus concentration equals 10 to the minus 7. And the OH concentration equals 10 to the minus 7. So when it's neutral, they're both the same. One's not more than the other. So if H plus equals 10 to the minus 7 and concentration of OH minus equals 10 to the minus 7. Okay, then they're equal, which means everything is neutral. That's at a pH equals 7. Okay, so this is all in water. This is when you have neutral reaction, neutralization, producing water. Okay, OH, and they're related by that equation. So if you know the H plus concentration of a water solution, you can calculate the OH. If you know the OH concentration, you can calculate the H plus concentration by the relationship that H plus times OH minus is always going to equal 10 to the minus 14. Okay, so from if the H plus concentration is 10 to the minus 3, so if H plus acid or base?
Acid.
Acid, perfect. It's greater than 10 to the minus 7. H plus concentration equals 10 Shoot, new pH. 10 to the minus 12, acid or base?
Not a basic.
Base. Right. If H plus equals 10 to the minus 7, acid, base, or neutral?
Neutral.
Neutral. So any number that's greater than 10 to the minus 7 for the H plus is going to be acidic. Any number that's less than 10 to the minus 7, like 10 to the minus 8, 10 to the minus 9, any number less than 10 to the minus 7 is going to be basic. Any number exactly 10 to the minus 7 for H plus concentration is going to be neutral. And the H plus times the OH is going to equal 10 to the minus 14. Okay. So let's do some equations with it here. But that's the basics for all your pH and everything right there. So if we're given any one, we can find the other one. So let's go from your book. Let's say concentration of H plus is 1.0 times 10 to the minus 6. So H plus is equal to 1.0 times 10 to the minus 6. Okay. What is the concentration of OH minus, hydroxide ion? Right. First of all, this solution is acidic or basic? Okay. Neutral is 10 to the minus 7. If it's
Acidic.
great, perfect. You got it. It's acidic. This is an acidic solution. Okay. We know H plus. I'm going backwards all the time here. We know H plus times OH minus is always going to equal 1.0 times 10 to the minus 14. So we're looking for OH minus equals 1.0 times 10 to the minus 14 divided by H plus. Just rearrange that, right? And we know the H plus concentration. So we got 10 to the minus 14 divided by 10 to the minus 6. We bring the exponent up and change the sign. Minus 14 plus 6 equals what? Ten to the minus. Weird computer. 10 to the minus 8. So remember, you bring this up, you change the sign. So you get minus 14 plus 6, and that's equal to 8. So the OH concentration is 1.0 times 10 to the minus 8. Does that make sense? I know it's the math part.
Yes.
But all you remember is this right here. H plus and OH minus are always going to equal 10 to the minus 14 for water. For any acid dissolved in water. So that's one of your formulas. So let's do one more, just to make sure you guys understand it. Let's say, let's go to another one here from your books. You go back to it. Find the H plus concentration. So let's say the OH minus of a calcium hydroxide solution is 4.3. Come on. 4.3 times 10 to the minus 7. Okay. What's the H plus concentration? We know the formula, H plus times OH minus is going to equal 10 to the minus 14. So we're looking for H plus. We divide by side by OH minus. 1.0 times 10 to the minus 14 divided by, what's our OH? 4.3 times 10 to the minus 7. Yep, that's our OH concentration, right? Now, if you got your calculators, you can use what's called the EE key, the exponent key. And if you have an iPhone, you go to your calculator. I'll walk you through the steps. You get your calculator that looks something like that, right? If you turn it sideways, you get a scientific calculator. Okay, so if you leave it that way, you get that calculator. Turn it sideways, it becomes a scientific calculator. So turn it sideways, and you enter 1 times 10 to the minus 14. So on your keyboard, you would hit 1, then you hit EE for your exponent, then you would hit 14, and then you would hit the plus minus sign. It's the third button from the top right-hand side. That gives you a minus 14. And then hit divide. Okay. Then hit 4.3. Okay. Then hit EE for your exponent. Then hit your exponent, which is 7, and change it to a negative sign. And then hit equals. And it comes out to 2.33 times 10 to the, then count your digits. 1, 2, 3, 4, 5, 6, 7, 10 to the minus 8. And that's how to do it on the calculator if you want to use exponents. Or if you want to do the way we did before, the way we've done before, you use your regular calculator. You could hit 1 divided by 4.3. That comes out to 0.233. And then this is 10 to the minus 14. And this is 10 to the 7. Okay, because that is, you bring this up, you change the sign. So it becomes 0.233 times 10 to the minus 7, or 2.33 in sign notation, times 10 to the, make that bigger, make this smaller, minus 8. And they're both the same answer. So either way you want to do it, you can do it. I mean, you might want to get used to using exponents because we're going to have to use a scientific calculator for logs when we do those for the pH. So if you're given the H, you can solve for the OH concentration. If you're given the OH, you can solve for the H. Just set not the summation, the multiplication of both those equal to 1.0 times 10 to the minus 14. So far, so good.
Yes.
All right. I think that'll help with a lot of the questions people had. It's just getting used to it, going through it. All right, pH. pH is used in all kinds of things. You need to know pH in any kind of medical profession. You want a clean pool, you'll know what pH is. pH is minus the log of the H plus concentration. That's it. Minus the log of H plus. That's what pH means. So POH is minus the log of the OH concentration. But we usually use it as pH. It measures the acidity of your blood, acidity of your swimming pools, acidity of whatever you want to work with. Because our enzymes work within a very small range of pH, like 4.2 to 7.2 to 4 to 7.3, something like that in that range. I'm pretty sure off the bat what the exact range is. But it works on a very narrow range. All right. So from a pH of 1 to pH of 2 is a 10-fold increase. pH of 2 to 3 is 10-fold. pH 2 to 4 is 100-fold. Okay. So it's going up by logarithm. Logarithm is powers of 10. Okay. So a pH, like I said, if it goes from pH from 2 to 3, that's a factor of 10. 2 to 4 is a factor of 100. 2 to 5 is a factor of 1,000. Okay? It goes up by groups of 10. 10, 100, 1,000, 10,000, 100,000, etc. Okay? That's your logarithmic scale. That's all log is. Logs is counted by powers of 10. Think of it that way. Okay? Now, we said that when the pH equals 7, H and OH are the same. So the concentration of H plus times the concentration of OH minus is equal to 10 to the minus 14. So when it's 10 to the minus 7 times 10 to the minus 7 equals 10 to the minus 14, this is equal, right? They're both the same. 10 to the minus 7, the pH equals minus the log of the H plus. In this place was 10 to the minus 7. Okay. If you use your calculator, turn it sideways to get your scale. Put in 10, put in 1 EE, negative 7, then hit equals, then hit your log. And it comes out to 7, because this is negative log. It comes out to negative 7, but this is minus the log. So minus negative 7 is 7. So this is pH 7. That's your neutral point. That's when H plus equals 10 to the minus 7. Okay. So in doing that on the calculator, remember, you have to hit equals before hitting log or you get an error sign. So you hit 1, EE, 7, change it to negative by the plus and minus signs. Okay. Hit equals, then hit your log. And you end up with negative 7. And it's the negative value of negative 7, which is 7. So that's your neutral pH, and pH is 7. Okay, so when you're looking at it like minus the log of 10 to the minus 3. 10 to the minus 3 is acidic, right? Because it's less than, it's greater than 10 to the minus 7. Okay. Minus the log of 10 to the minus 3 gives you a pH of 3. So when the numbers go down on the pH scale, it's getting more acidic. Okay. When the numbers go up, it's becoming more basic. So pH greater than 7 is basic. A pH less than 7 is acidic. Okay. So now pH of 3 is very acidic. And that's 10 to the minus 3. Okay, is that making sense? So we'll do some of the pH values. So the two equations we had was the H plus and OH minus is 10 to the minus 14. We got pH is minus the log of H plus concentration. That's one right here. Okay. So we know the pH, we know our pH plus our POH is always going to equal 14. Okay. Remember the H plus concentration and the OH minus concentration, okay, is equal to 1 times 10 to the minus 14. Okay. So if you do the pH of both of them, the pH and the POH are going to equal 14. So if you know the pH, you know the POH. And P just means minus the log of whatever concentration that is. Okay, so let's summarize the formulas. We have H plus times OH minus is equal to 10 to the minus 14. We have pH. pH equals minus the log of the H plus concentration. We have POH equals minus the log of the OH concentration. And we got pH plus POH equals 14. That's what we talked about so far in the dealing with H plus concentration. Okay. Those 4 statements make sense. If those make sense, you can solve any problem. As long as those make sense to you. Okay, questions on either of those four statements? Because if we understand that, we'll understand everything else. Okay. Let's try. We get all that. What is the pH of a solution if the pH is 9.3? Binding lights. Okay, we'll do a couple of these. All right. So we have those solutions that we know, right? So pH of a solution is 9.3. Okay. Is it acidic or basic? Someone tell what?
Basic.
Basic, perfect. It is. It is greater than 7. Okay. Greater than 7 is basic, less than 7 is acidic. Okay, what is the OH? POH. POH is what? POH plus the pH equals 14. So POH equals 14 minus the pH, 14 minus 9.3. So the POH is, where are we at? 3, 4, 4.7. Okay. So you can solve the H plus concentration. You can solve the OH concentration. You can solve the pH and the OH. Okay. If you know the pH is 9.3, you can go backwards and solve for the H plus concentration. Okay. Let's do one that says example 12.7 in your book. Finding H and OH from the pH. There we go. Perfect example. Okay. Carbonated soft drinks. Okay, basic Coca-Cola. Her pH usually between 2 and 3. Okay. That's pretty acidic. So let's say the pH is equal to, well, I'd rather do when you have to do some calculations. Let's say the pH of a solution is equal to 2.73. Okay. I want to find the H plus concentration, and I want to find the OH concentration from that net value. Okay. First step is to get the H concentration, right? Because you know the pH equals 2.73. pH equals minus the log of H plus equals 2.73. Okay. So the log of the H plus is equal to negative 2.73. And move the negative sign to the other side. The inverse of the log on your calculator, okay, is 10 to the x. That's the exact opposite of log. So that's a key to look for if you want to do the inverse of a log. So take the inverse of the log on both sides. Okay, so you'd have with equals 10 to the negative 2.73. So on your calculator, how you would hit it, okay, go to your scientific notation. You would go to 2.73, and you hit the negative plus and minus sign, switch the sign to negative, okay, and you hit the inverse log, which is 10 to the x, and that comes out to 1.86 times 10 to the negative, and that's going to be 10 to the negative 3. Okay, so now you got your H plus concentration. So all you do is enter your number, and then you hit inverse log, which is 10 to the x. And that gives you H plus concentration. From the H plus, I can find my OH. My OH concentration, okay, is equal to 1.0 times 10 to the minus 14 divided by my H plus, which I just calculated. 1.86 times 10 to the negative 3. Again, if you want to use your scientific notation and if your scientific calculator, you could put 1 EE and then minus 4 and then 14 negative divided by 1.86 EE and then 3, change the sign negative, equals 5.38 times 10 to the, where am I at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 10 to the negative 12. Double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. Okay. So from the pH, I could find the POH, just subtract 14. I could find the H plus concentration by taking the inverse log. And I can find the OH concentration. Let's 10 to the minus 12. Do that right. 10 to the minus 12. There we go. So starting with our pH, I can find the H plus, I can find the OH minus, I can find the POH. You know, one of those facts that we went over before. Okay. And let's see what else I've got on here. Okay, baking soda. Okay, let's do one more. We'll do one more from your book here so you have one to compare it to. All right, let's do baking soda. Baking soda water is a pH of 8.3. What is the H plus concentration? Okay, so pH is equal to 8.3. Acidic or basic?
Basic.
Basic. So you know, if your answer comes out to greater than 10 to the minus 7, you know it's wrong because it has to be basic. The H plus concentration has to be less than 10 to the minus 7. Okay. This pH is 8.3, so this has to be basic. So it has to be less than 10 to the minus 7. Because if it's greater than 10 to the minus 7, it's acidic. So it's going to be less than 10 to the minus 7, your H plus concentration. Okay. So pH equals 8.3. pH equals minus the log of the H plus concentration is equal to 8.3, right? That's what our definition says. So we put minus on the other side, the log of H plus is equal to minus 8.3. And then we just do 10 to the X to both sides, get rid of the log. We have our H plus concentration is equal to 10 to the X of negative 8.3. So on our calculators, we turn it sideways and we hit 8.3, and then we change the plus negative sign to negative, okay? And then we hit 10 to the X, which is usually right above your log key. And you get your answer of 5.01 times 10 to the negative 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the minus 9. Okay. And that's less than 10 to the minus 7. So that's a good check for us right there. Okay. That's how you do pH. That should have cleared up a lot of the questions. We'll still go over a lot of the questions anyways. Okay. And then determining, we got one more section to do, and that's determining acid and base concentrations in the lab. Okay, we can use liquid paper, we can use paper that turns color with different acids. Like we can check the pH of a pool. You'll see they take the pH, they'll put the water and shake it up, and they'll dip a stick with chemicals on it. and then compare the color. The color changes depending on the concentration of H+. And that tells you the hydrogen concentration in the pool, whether it's safe to swim in, whether the chlorine ions at certain levels or not, or whatnot. And we do reactions in labs that mix an acid and the base. We determine what concentrations, what volumes that we need. Okay. Now, anytime we have a neutralization reaction, we have the formula. We're mixing an acid and a base. M1V1 equals M2V2. Does that sound familiar? That's our dilution formula. Same thing. Okay? But with acids and bases, it's Ma for acid, Va for the volume of acid, M2Mb for base, Vb. So MaVa equals MbVb. Same exact thing as M1, M2 equals M1V1 equals M2V2. Same exact thing. Just what we did with dilution, because that's what we're doing. We're diluting an acid until it becomes neutral. We're diluting a base until it becomes neutral. It's a neutralization reaction. So it's going to be the same formula. So if we know the concentration of the acid and the volume that we're going to use, we know how much volume it reacts with, we know the strength and concentration of the base. Okay? If we know 3 of the variables, we can solve for the 4th. And these was called titration experiments. Okay? So let's do example, let's see, 12.9 in your book, so you can follow along with it if you want. So that's our only formula for dilution, which is neutralization is a form of dilution. So you can use the same formula. Okay, so it says a 25 milliliter sample of hydrochloric acid. So you have a 25 milliliter sample of hydrochloric acid. Okay, is neutralized. We're going to react it with, okay, by a reaction with 17.4 milliliters of 2.00 molar sodium hydroxide. Okay. So we started off with 25 milliliters of hydrochloric acid in a little bowl, and we dumped in drops of sodium hydroxide to neutralize it. And it took 17.4 milliliters to neutralize it. Okay, so it wants to know what is the concentration of the hydrochloric acid in our sample. Okay, how strong was it? And we know the formula. M of the acid, V of the acid equals M of the base, V of the base. Okay, so M acid, M base, V acid, V base. M of the acid is, that's what we're looking for. Molarity of the base is 2.00 molar. Volume of the acid is 25.0 milliliters. Volume of the base is 17.4 milliliters. There's our numbers. And all we can do is rearrange our formula and plug them in. Okay, so we're looking for Ma. Ma is equal to molarity of the base, volume of the base, divided by volume of the acid. Just rearranging our numbers there. Okay, plug them in. 2.0 molar. Volume of the base is 17.4 milliliters. And volume of the acid is 25 milliliters. Make sure your units are the same. Make sure your milliliters, so the milliliters cancel. And the molarity of the acid is going to be 2. Okay, it was 2 times 17.4 divided by 25. That equals 1.39 molarity. That's the concentration of your acid. What's up?
Okay.
Okay. So you can do any dilution experiment or any neutralization experiment, titration, and solve for one and give the other. Okay. Let's find another good example. Now, that was HCl and NH. That's a one-to-one relationship. The only time it's be different is the balanced chemical equation is different. In other words, your equation was hydrochloric acid plus sodium hydroxide goes to NaCl plus OH minus. I mean, NaCl plus H2O, sorry. Okay. Everything's a one-to-one relationship. Yeah, it's a balanced chemical equation. Now, if the reaction is different, if 1 mole goes to 2 moles, you got to account for that because it's a balanced equation as you're titrating it. Okay, so all you got to do is consider. Let's consider the reaction of H2SO4. Sulfuric acid plus, let's say, potassium hydroxide goes to the salt, K2SO4 plus water. Balance reaction, 2 OHs and 2 waters. That's rebalanced. So now look at the difference here. This is 1 to 2 relationship. Okay, you have to account for that because it's a molar equivalent as you're dropping it in to neutralize it. Okay? So it's still the same equation, except you're going to add a coefficient, okay, in front of each one. So if it's different numbers, different values of moles, okay, it's going to be M over VA over molarity of base times the volume of base. And both these are going to be divided by the coefficient of the acid, the coefficient of the base. The coefficient just means this number right here in front of the compound. Okay, so that's CA and CB, coefficient. And remember, if there's nothing there, it's a 1, it's not a 0. Remember, this right here is a 1, it's not 0. Because when 1's there, we just don't include it, okay? So that's the only difference. When your reaction involves different balanced coefficients from your balanced equation, then you got to account for that because it could be a different molar relationship as the reaction is occurring. And you just divide by that coefficient on each side. So let's take our reaction here, and let's say this is example 1211 in your book. Okay, let's say we have a 50 milliliter sample. .0 milliliter sample of sulfuric acid. Okay, is neutralized by potassium hydroxide solution. Okay, that's 0.400 molar potassium hydroxide, KOH. Okay, 0.4 molar. If 22.6 milliliters of KOH are required to neutralize, what's the concentration of sulfuric acid solution? Okay. Same thing, we're looking for the concentration, the molarity, okay, of the acid. So Ma is equal to, let's put this back here, molarity of the base, volume of the base, divided by concentration of the base. And we're going to divide by the volume of the acid, and we're going to multiply the concentration of the acid, the coefficient of the acid. Okay. So there's our values. We have everything we need. Okay. Molarity of the base is 0.400. The volume of the base was 22.6 milliliters. The coefficient of the acid was 1. Coefficient of the base was 2. Volume of the acid was 50 milliliters. Okay. Does everybody look at how that's set up? Okay. So it's 0.4 times 22.6 times 1 divided by 2 divided by 50 equals 0.0904. And that's the molarity of your solution. That's the molarity of the acidic solution that you started with. It's the same formula we've been using, but you got to take into account the difference of moles being transferred if it's in a balanced chemical equation. So it's MAVA over MAVA each divided by the coefficient of each number in the balanced chemical equation. Okay. Let's do one more. Let's pick on, let's see. What volume of 2.4 molar aqueous sodium hydroxide is required to completely neutralize 200 milliliters of 6 molar aqueous hydrobromic acid? Okay, so let's write down the numbers we have here. And we've got, okay, so what volume of 2.4 molar NaOH? So we have NaOH, and we have 2.4 molar. We want what volume? Okay. To completely neutralize 200 milliliters of HBr. 200 milliliters, 200.0 milliliters. Okay. And we've got what else we got? 6 molar HBr. Okay. So sodium hydroxide and HBr is a 1-to-1 relationship. If you do the equation out, it's all going to be 1-to-1 because everything's reacting. NaOH plus HBr goes to NaBr plus H2O. That's a balanced chemical equation. The coefficient in front of each one is 1. So we don't have to worry about the coefficients for this one, right? For this a 1-to-1 relationship. So it asks, what volume of a 2.4 molar solution of sodium hydroxide, which we got there, okay, is going to react completely with, to neutralize 200 milliliters of 6 molar HBr. Okay. So we have molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. And we're looking for the volume of the acid. Volume of the acid is equal to the molarity of the base times the volume of the base divided by the molarity of the acid. Okay. Once you set up, now the numbers are easy once you set it up. Setting it up is the hard part. Okay. So let's put the numbers in. Molarity of the acid was, wait, did I do it backwards? We're looking for the volume of the base. I'm sorry about that. Let me back that up a little bit. This is what we're, volume of the base. Okay. This is our base. Okay, this is going to produce OH minus. It's going to be a proton donor. The other one's this will be a proton acceptor. Okay. So this is our base. We're looking at the volume of the base. I'm sorry. So the volume of the base is equal to the molarity of the acid times the volume of the acid divided by the molarity of the base. So the molarity of the acid is 6.0 molar. The volume of the acid is 200 milliliters. And the molarity of the base is 2.4 molar. Molarities cancel, you're left with milliliters. So you get 6 times 200 is 1200. 6 times 200 divided by 2.4 comes out to 500 milliliters. And that's your answer. Does that make sense?
Yes.
All right. I think that's the end of the chapter. Let me check. Is there one more section after this one? Oh, there's one more section of this one. This is a long chapter. pH and buffers. All right. So now we know what the pH is. We know our body works on pH. We know conjugate acid, conjugate bases. There's a mixture. And basically, our body's a buffering system. We have carbonic acid that floats in our bloodstream. So carbonic acid we saw has a conjugate acid and a conjugate base, and it can go both ways. If an H plus is added, it can reverse it. If an OH minus is added, it can reverse it. So it allows us to buffer our bloodstream. Okay? It's the same principle like in aspirin, where you can use that as a buffer. Okay? So let's show how bicarbonate works in the bloodstream. Okay, it's carbonic acid, H2CO3 plus water, H2O. It went to HCO3 minus plus H3O plus. Okay, so if we add, okay, so that's what carbonic acid does in the blood, right? It breaks down. So if I add H plus to the system, okay, this ion here, we can take, if H plus is added, like something acidic comes into your body, you get an infection and it starts making it more acidic. H plus increases in your bloodstream. And we can't have that because then the enzymes aren't going to work and your body will cease to function. So the H plus in the blood reacts with this ion here, HCO3 minus, to go back to carbonic acid and absorb some of that H plus. Okay, if the bacteria or the infection produces OH minus. Okay, OH minus can react with the H3O plus, which is this right here, to form H2O. Okay, because it takes the hydrogen back off and forms H2O, which neutralizes it. So whether you add H plus in our blood from an infection or the infection adds OH minus, we neutralize it. It's called a buffering solution. It means if you add H plus, the effects are not going to change that much. If you add OH minus, the effects are not going to change this much. And this is a conjugate acid-based system that we use to buffer our bloodstream and does not allow our pH to go too low, which means it gets too acidic, or too high, which means it gets too basic. Because either way is bad for you. You see all these commercials that they want to increase your body's or increase your body's basicity to help make you better. No, you can't. You cannot change your blood pH. It's in a very narrow range, 7.3 to 7.4, something like that, or 7.35 to 7.45. Your blood pH is 7.35 to 7.45. If it goes out of that range, you're in trouble. Because all your enzymes, just break down your food, provide your body with energy, build your proteins. All of your enzymes work in that pH range. If that pH range changes, then those enzymes stop working. And your body dies. So these buffering systems are extremely important. So all buffering means is if you add H plus, like an acid, it tones it down. So it doesn't go increase the H plus too much. If you add OH minus from a base, it tones it down, it absorbs some of it. So you don't increase your basicity that much. And it keeps it in a narrow range. Okay, aspirin. Aspirin is acetylsalicylic acid. It produces acid in the body. It causes heartburn, it causes all kinds of things. Okay, that's why they came out with buffering. Buffering is a buffered aspirin product. It has a conjugate base in it, so when it goes in the body, the H and the OH are absorbed, so it doesn't alter the pH drastically in the body. It doesn't cause all those things like that. That's when buffer was produced. Okay, so that is your buffering system. That's what this whole section is about. Okay. Let's do one problem. Let's make sure everybody understands it right. Let's do a common buffer is prepared from citric acid. You can use citric acid, carbonic acid, any acid has a weak conjugate acid come back with. All right, so let's say we have a buffer for citric acid. Okay, which one of the combinations would be the most effective buffer? We could use a 0.01 solution of citric acid and its ion, of citric acid, and a 0.01 citric acid, citrate, I just put C for citric ion. So there's the acid and there's the ion in the reaction. Or this is 1, 2 would be a 1 molar solution and a 1 molar ion. 1 molar of the citric acid, 1 molar of the ion. Okay. Or 3, 1 molar of the acid, or 0.01 molar of the ion, or 0.01 molar, or 1.0 molar of the ion. Okay, to be effective, okay, look at the chemical reactions. That's with carbonic acid. It's a 1-to-1 relationship. So to be effective, they've got to balance 1-to-1. The concentrations have to be about the same, so the reaction can go either direction. Absorb H plus or get rid of H plus. Okay? Decrease the pH or increase the pH. So they got to be the same to make it most effective. Okay, so this one's the same and this one's the same. Now, the greater the concentration, the greater the buffering capability, the more there is to buffer. So the higher one is going to be this one. So this would be your greatest buffering or most effective buffering solution. They're both the same and it's higher. It's got more around to buffer. Does that make sense?
Yeah.
That's all it is. That's all a buffering solution is in the body. It just allows a conjugate acid to go both directions and absorb. So your H plus doesn't, your pH doesn't vary, or it doesn't vary any significant amounts, whether you get real acidic from an infection or real basic from an infection. All right, that is the end of chapter 12. Any questions on chapter 12? If not, we can go over some of the questions. Let me pull up my emails. All right, so let me close this and start with some of the emails that were asked. And she modified some of them, so where my emails go? Pull back up. Since I don't have them here. All right, let me put my emails right here. So I'll put it on this side. And this is a modified list. So let's look at this one. We might have answered some of the questions here already, but let's go through these. All right. There's just a couple here because I think we covered most of the other ones. It says calculate the H plus and the pH of a solution with an OH minus of 0.0065 molar at 25 degrees centigrade. Okay. So it wants you to calculate the H plus concentration. So we're looking for the H plus concentration and the pH. Okay, calculate the H plus and the pH of a solution that has an OH minus concentration equal to 0.0065 molar. Okay. So we can calculate the H plus, we can calculate the pH. We know that H plus times OH equals 10 to the minus 14. So we know we have that equation. Okay, so we have the OH, we can calculate H plus equals 1.00 divided by OH. Rearranging our equation, we have 1.00 times 10 to the minus 14 divided by, we know our OH concentration of 0.0065. Okay, so let's do our calculations. Let's do the scientific notation ones. Let's turn our calculator sideways, or function if you have, or you use calculate with an EE function. Same thing. We put in 1 EE 14 and then change it to a negative sign. Then we hit divide. In this case, it's 0.0065. And it comes out to 1.54 times 10 to the negative, and we count the zero. Like, it doesn't put inside notation, just keeps all the zeros here. 1, 2, 3, 4, 5. It's like 12. I'll double check that though. 1.54 times 10 to the negative 12. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. So our H plus concentration is 1.54 times 10 to the minus 12. Once you have the H plus concentration, now we can have the pH. pH equals minus the log of the H plus concentration. So minus the log of 1.54 times 10 to the minus 12. So again, we take, and there's only one little trick here when you're dealing with logs like this. If you put in 1.54, 0.54, and then EE, and then 12, and then hit the plus minus conversion, change it to a negative. When you're dealing with logs now, you have to hit the equal sign here to set that equal to the number. When you're using EE, you just got to equal that number, so hit equals, that gives you your number, and then hit the log. And then reverse the sign, hit the negative sign, and it's 11.8 is your pH. So that's the H plus concentration, and that's your pH. Does that make sense? Thumbs up, yes, something. Some don't make sense to me doing that.
Yes.
Yep. All right, perfect. And the other one was calculate the H and OH of a solution with a pH equal to 2.17. So let's do that. And those are the only two questions for that. And then I have another email too. So let's do that one. Okay. So I have a pH equals 2.17 at 25 degrees centigrade. So there's your pH. So let's calculate the H plus concentration. We can do this two ways. Let's do it this way. All right, so pH means minus the log of H equals 2.17. So that means the log of H equals negative 2.17. So we do the inverse, get rid of the log, which is 10 to the x. It's the inverse of log. Again, use your scientific calculator. Turn it sideways and put in. We have put 2.17 negative, okay, and then hit 10 to the x. And it comes out to 6.76 times 10 to the negative 1, 2, 3. That's your H plus concentration. Remember, your OH was H times OH gives you 10 to the minus 14. So your OH is going to equal 10 to the minus 14 divided by 6.76 times 10 to the negative 3. So again, we do our scientific calculator. We'll put in 10 to the minus 14. So 1 EE 14 negative divided by 6.76 EE, and then this is 3, then change the sign to negative. It equals 1.48 times 10 to the negative something here. Let's count the zeros here. So there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10 to the negative 12. So here's your H plus concentration. Here's your OH concentration. Does that make sense?
Yes.
Okay, perfect. Now, just remember, if you remember that in a water solution, that the concentration of H plus times the concentration of OH equals 10 to the minus 14. The POH plus the pH equals 14. Okay, and minus the log of the H plus concentration equals the pH. Those are the only things you got to remember in dealing with concentrations. And you can solve any of those problems. Okay. Then I had another email here. Cool. All right. 30 milliliters of sulfuric acid solution with unknown concentration was titrated to a phenolphthalein endpoint with 35.7 moles of sodium dioxide solution. All right. This one you have to remember. This one it's going to have a different balanced equation, different coefficients on this one. That might be what messed people up here. So let's take a look at this one. So always write out your equation to start with. So sulfuric acid, H2SO4, plus, and you're using sodium hydroxide to neutralize it. It's going to give you your salt and water, sodium sulfate, Na2SO4, plus water. And we got to balance this puppy. Two sodiums. 1, 2, 4 hydrogens. 4 hydrogens. 1 sulfate, 2 sodiums. That's it. Oxygen, so 4, and 2 oxygens, we're good. All right, now we're balanced. So you notice we have different coefficients in dealing with our equation. So molarity of the acid, volume of the acid, divided by the coefficient of the acid equals the molarity of the base times the volume of the base divided by the coefficient of the base. So there's our equation. We just got to figure out what we're looking for. Now we're given 30 milliliters of the acid. So let's go H2SO4. We'll put H2SO4 over here. And we got 30 milliliters of it. That's what we're starting with. It says 30 milliliters of H2SO4 solution with an unknown concentration. So we don't know the concentration. So unknown molarity, unknown concentration. Okay, it was titrated. It was mixed with phenolphthalein endpoint, which means it was an indicator with certain color. Okay, 35.17 milliliters of a 0.1301 molar solution of sodium hydroxide. So the base, sodium hydroxide. And we were dealing with 35.17 milliliters was used, and the concentration was 0.1301 molarity. That's all the information. And it wants to know the concentration of H2SO4. So we're looking for the concentration, the molarity of our acid. Okay, so the molarity of the acid, equals molarity of the base times the volume of the base divided by the coefficient of the base. And then times the coefficient of the acid, we move that up, and the volume of the acid, we move that down. And there's our equation. We rearrange this thing here. We move this one up, we move this one down to leave this by itself. That's all we did. Okay. We just plug the numbers in. Molarity of the base is 0.1301. Molarity. Volume of the base is 35.17 milliliters. The coefficient of the acid The acid is H2SO4. What's the coefficient of the acid? Look at the balanced chemical equation. What number is there?
1.
1. Perfect. Don't say 0. It's 1. Whenever there's nothing there, we always know it's a 1. Do not make that mistake. Okay. Coefficient of the base is a 2. And the volume of the acid is 30.0 milliliters. Milliliters cancel. The coefficient cancel left the molarity. So we take 0.1301. .1301 times 35.17 divided by 2 divided by 30 equals 0.0763 molarity. Okay. Actually, there's 4 significant digits. I left off a digit. No, 30. No, it has 30.00. Sorry. So it should be 0.7626. So it should be 0.07626 molarity. Sorry about that. Everything has four significant digits. You have to answer as 4 significant digits. So 0.0726. Does that make sense?
Yeah, it does. See, I was putting 0.0763 as my answer, and that's why I was wrong.
Yep. I did the same thing, so don't feel bad. But I just looked up and saw that and went, wait a minute. It's 4 significant digits. 30, because I put, right here, I messed up. I put 30.0, it's 30.00. So easy mistakes to make, but make them now. Don't make them on the midterm. Or on the final. Midterm is too late. By titration, next one on the email. By titration, it's found that 72.7 milliliters of 0.13 molar solution of sodium hydroxide is needed to neutralize 25 milliliters of hydrochloric acid. Calculate the concentration of the hydrochloric acid solution. Same thing. This one is 1-to-1 though. HCl and NaOH, it's 1-to-1. So you're going to use a formula. Molarity of the acid, volume of the acid equals molarity of the base, volume of the base, and you do not need to worry about the coefficients because they're all 1. Okay, so it's found that 72.7 milliliters of sodium hydroxide. So let's start with our base, NaOH, and 72.7 milliliters of a 0.135 molar solution of the base is needed to neutralize 25 milliliters of the acid. The acid is HCl. 25.0 milliliters of the acid. Calculate the concentration of the acid. Okay, we're looking for the molarity of the acid. Molarity of the acid equals molarity of the base, volume of the base, divided by the volume of the acid. Let's rearrange my equation, right? Plug my values in. Molarity of the base is 0.135 molar. Volume of the base is 72.7 milliliters. And the volume of the acid is 25.0 milliliters. Milliliters cancel, left with molarity comes out to 0.135 times 72.7 divided by 25 equals 0.393 is what I get. 3 significant digits. Does that one make sense?
Yeah, it does. Thank you.
All right. Oh, no problem. And another one is, what is a hydrogen ion concentration? pH 5.7. Again, our pH is equal to 5.75. So minus the log of H plus equals 5.75. Log of H plus equals minus 5.75. H plus, take the inverse of the log on both sides, which is the 10 to the x key. So this one you do have to use your scientific calculator or your iPhone with turning it sideways. So you take 5.75, change the sign to negative, and then take 10 to the x, hit 10 to the x, and you get 1.78 times 10 to the, and this, oops, I lost the negative sign on here. Let's see. Turn, okay. 1, 2, 3, 4, 5, 6. Let's say 6. 1, 6. And from that, you can get your OH. Now you get the POH. Okay. Does that make sense?
Yeah. Thank you. I just didn't know how to use a calculator.
Yeah, that's the problem with, that's what I feel a lot of people would have. Because you don't use logs that often. Just got rid of the inverse of the log is 10 to. Does it make sense now using the calculator?
A little bit.
Let me know if you need, what are you using, an iPhone or using a real calculator?
I'm using a real calculator. So this
Okay.
is the calculator I'm using.
Okay, but you have sign notation, the EE button, right?
I don't see it.
It should have EE or EXP.
No, but I have it on my phone, so I could just use my phone for this.
Okay. But it should have an exponent button on your calculator, on a scientific notation calculator.
Okay, yeah, I see it.
You found one?
Yeah.
All right, it's either EXP or EE, they're the exact same thing.
Okay.
Perfect, good. All right, so we got that. And one more. It says classify each aqueous solution as acidic, basic, or neutral. 1, 2, 3, 4, 5, 6, 7, 8. Is there more? There's one more question after this one too. Okay, the conjugate acid bases. All right, so let's look at this. And let's make columns. Let's make a neutral column. Let's make an acid column. And let's make a basic column. And pH equals 7. Neutral, acid, or base?
Neutral.
Neutral. pH equals 7. The OH minus equals 5.8 times 10 to the negative 2.
Acidic.
That's OH concentration, not 8. The OH concentration is 5.10 to the negative 2. So that's a strong OH concentration, which is a, what's OH? Acid or base?
Base.
Base. Okay. H equals 1.0 times 10 to the minus 7.
Neutral.
That's OH. I forgot to put OH here. That's H plus. Neutral, perfect. This is your OH minus here. Okay, and H plus equals 2.8 times 10 to the minus 10. Remember, if it's less than 10 to the negative 7, it's basic. Greater than 10 to the negative 7, it's acidic.
Acidic then?
Basic. It's less than 10 to the minus 7. 10 to the minus 7 is your neutral point. Remember, pH and the concentrations are exact opposites. They're negative logs. So the H plus concentration would be equal to 2.8 times 10 to the minus 10. Okay, we'll go with a little bit more here too. OH equals 5.1 times 10 to the minus 9. would be what? Would be acidic. Where are we at? 5.1 times 10 to the minus 9. Okay. H plus 7.6 times 10 to the minus 3. Ten to the negative 3 would be
Acidic.
acidic. Perfect. And pH 11.24, acid or base?
Would it be base?
Yep, it sure would be. pH is 11.24. And last one, pH equals 1.74, acid or base?
Acid.
Acid. Perfect. All right, so you look at all these numbers. The pH are easy. If a pH is 7, it's neutral. If it's less than 7, it's an acid. Greater than 7, it's a base. Now the problem comes with the concentrations. Remember, 10 to the negative 7 is your midpoint. So an H concentration or an OH concentration of 10 to the negative 1 times 10 to the negative 7 is neutral. If it goes above or below, if the H concentration goes up, it's acidic. If it goes down, it's basic. Okay, if the OH concentration at 10 to the negative 7 goes up, it's basic. Goes down, it's acidic. So a low OH. Okay, so yeah, so let's look at this. So this is your neutral. H concentration is greater than negative 7, right? So it's acid. Okay. The OH concentration is less than negative 7. That means the H plus is greater than negative 7, which means it's a base. Remember, H plus times OH is always going to equal 10 to the minus 14. Okay, so if the OH concentration is low, means the H plus is lower than 7. It means the H plus is greater than 7, which is acid. Okay, and pH is above 7. That's a base. H plus is lower than 7. That's a base. OH minus is very high there, 10 to the negative 2. That means it's greater than 10 to the negative 7. So that means an H plus is less than 10 to the negative 7. Okay, so it's going to be basic. So that's the logic behind all those. Does that make sense?
Yeah, it does.
Okay, it's just you got to think it through sometimes. Okay. The conjugate acid of H. Okay, so this is to identify conjugate acids, and these are all conjugate acids. Okay, so let's do conjugate acids. Let's do. Let's move this to here. So. Okay, HSO4. And you want to know the conjugate acid. So let's show that in and that with water. Goes to SO4 2 minus. Oh, come on back. Plus H3O plus. Right? We donate the H plus. Okay. This is our acid. What is that to the base? Conjugate means reverse reaction. So look at the reverse reaction. What is the conjugate acid? Which one is the acid? SO4 2 minus or H3O plus? Which one is the acid? Which one donates a proton, gives an H plus to the other one?
The H3O is the acid.
Got it. This is your conjugate acid. Okay, perfect. And then PO4 3 minus. PO4 3 minus is your phosphate ion plus water goes to it has to donate protons. So this goes to H, PO4 2 minus plus OH minus. Okay, you get the acid goes there. So which one is the conjugate acid? Which one here donates a proton?
The OH.
No. Which one gives a proton to the other one?
Mm,
This proton goes here to form H2O, right?
right.
So this is your conjugate acid. It gives up a proton. Does that make sense?
Yeah, it does.
This one accepts the proton over here. Okay, and the other one is NH3 plus H2O goes to NH4 plus OH minus. Okay, so this is your base, this is your acid. And then which one here donates a proton? NH4 plus or OH? Which one gives up a proton? Loses a hydrogen?
OH.
And
OH,
it-
huh?
is it OH?
No, OH accepts a proton.
Okay, yeah, then it's
This-
another one.
Right, one of the protons goes here to form water. Then we get backwards reaction. Okay, so this is your conjugate acid. And this is your conjugate base.